All right, so we're moving into section 5.1, and a very important topic, 5.1, eigenvectors and eigenvalues. Okay, and I want to just do an example. Again, I could, go into the book. This is actually an example from the book, but I think it's a very nice example, and I think I think it's just a good, nice example to do. So I'm giving you a matrix here, a square matrix A, and I'm going to say that an eigenvalue of A is lambda equals 2. Okay, what's an eigenvalue? You'll know in a minute. And then we want to find a basis. We know what a basis is for the corresponding eigenspace. Okay, so just go ahead and copy the example down, and then I'll work through the solution, and it'll make sense to you. All right, so we have this matrix A, and you're being told that an eigenvalue of the matrix A is lambda equals 2. We want to find a basis for the corresponding eigenspace. But before we know how to do this problem, we better know what an eigenvalue is. Well, to understand an eigenvalue, you also need to understand what an eigenvector is. So let me go to the solution. Are we good? May I move to the next page? Okay. Okay. Thank you, Christy. Thank you, Solomon. All right. So just like like you would find a null space of a null space of a matrix, or a column space of a matrix, there's a space called an eigenspace of a matrix. Now, the matrix has to be a square matrix for it to have an eigenspace, but we have a square matrix. So what we do is the eigenspace consists of eigenvectors. But what's an eigenvector? Well, here's the key. Here's the key. Matrix equation A times the vector x equals lambda x. And lambda, of course, is some scalar. Lambda is a scalar. That is how eigenvectors and eigenvalues are defined. If you take a matrix A times a vector x, and that transformation equals a multiple of the vector x, then we call the vector x an eigenvector, and we call the scalar lambda an eigenvalue. Okay, so any vector x that satisfies the matrix equation ax equals lambda x, any vector x that satisfies that will be in the eigenspace of the matrix A. So what we have to do is we have to find these eigenvectors. Well, this is somewhat similar to what I showed you in section 4.9. where we had to find the steady state matrix. We have a matrix equation, AX equals lambda x, but on the right side, lambda x, I write it as lambda times, in this case, it would be I3, right? Because it's a, x is a 3 by 1. But we would write lambda times x as lambda times the identity matrix times x. Okay, and then we'll subtract this term here, this term, the whole term, we'll subtract to the right side. And so we'll get a times x minus lambda times the identity times x equals 0. Okay, I want to solve for x. So I'm going to factor x out on the right, of course. Okay, so a minus lambda I times x equals the 0 vector. And this here is the matrix equation that I'm going to solve. That's the matrix equation I'm going to solve. Well, okay, we were told in the problem that lambda equals 2. We were given that. Now, we're going to learn how to find these eigenvalues. Here they're telling us the eigenvalue lambda equals 2. And so I'm going to solve the augmented matrix A minus 2i, 0 vector. And so A minus 2 times I, okay, that's computed as you see here. I'm taking the elements of the matrix A and subtracting them by the elements of the identity matrix, 3 by 3 identity. And this is going to yield me this system down here at the bottom. Let's see, Noah says for steady state, that is correct. Noah says for when you find a steady state vector Q, okay, for the steady state situation that we saw, we wanted to find Q such that M times Q equals Q. Well, in fact, we can put a 1 in front of the Q, the scalar 1. Sorry, let me get that nice. I can get that nice. I mean, we know there's a 1 understood to be there. And so the steady state vector Q is in fact an eigenvector of the matrix M, the migration matrix M. Absolutely. Now that's an example, but of course here we're doing well, yes, that's right. So now for our problem then, we have this augmented matrix here. Okay, and gee, does that look hard to solve? No, I don't know what this stuff is here. I'm gonna just scratch that out. That shouldn't be there. Not hard. So let's go to the next page and finish it. Okay, that's right, Solomon. 2 free variables. Okay, so I added the first row to the second row, replace the result. I mean, I'll put in the instruction here. Why not? Took row 1. Hold on. Okay, I took row 1 plus row 2. Put the result in row 2. And then I took row 1. Thank you, Solomon. That's right. I took negative row 1 plus row 2. and put the result in row 2. And then I took negative row 1 plus row 3 and put the result in row 3. And then this gives me this matrix for which x3 and x2 are free. Then the top row here would be, gosh, sorry, I'm going to just try to slow down a little bit here. Okay, so the top row will yield that 2x1 equals x2 minus 6x3. Hence, x1 is a half x2 minus 3x3. So I'm going to write this vector x in parametric vector form. I'm going to write it in parametric vector form. And I always like to put in my entries to x. Sometimes students will go from the vector x right, they'll go right to the parametric vector form here. But that is, you're asking to make an error when you do that. Okay, always best to put in, your entries. How many find that to be true? Put in those entries and then go to the parametric. And yes, Matthew knows what I'm talking about. Okay, all right. So we have a basis for the eigenspace. So really, remember what you're doing here. Remember what we solved here. We solved this. We solved A, the augmented matrix, A minus 2I with the zero vector. So really, the eigenspace is equivalent to finding the null space of A minus lambda I, or in case A minus 2I. So we have these two vectors here. We have these two vectors, and they're going to form the basis for my null space. But if you don't mind, since the first vector is a half 1, 0, is it okay to write 1, 2, 0? The second vector is negative 3, 0, 1. But is it okay? Would the basis span by the vectors 1 half 1, 0 and negative 3, 0, 1 be the same as, I'm going to say this right, would the span of the basis vectors a half 1, 0 and negative 3, 0, 1 be the same as the span of the vectors 1, 2, 0 and negative 3, 0, 1? Would it be the same? It would be. All you're doing is the first vector, you're multiplying it by 2. Okay, a multiple. So that doesn't, the vector still points in the same direction. Half 1, 0, that vector points in the same direction as, the 1, 2, 0 vector. Okay, and I want to just show you this figure real quick. So bear with me just 1 or 2 minutes more. I appreciate it, I do. Are we okay here? Are there any questions? Okay. Okay. Well, now what I want to do is there's a nice figure in 3 from section 5.1 that I want to show you. So let me bring it up here. Okay, let me bring it up here. One moment. Right. Okay, so this here, this figure, it is the, you know, this example I'm doing is from the book, but what you're seeing here is a figure where it shows that A acts as a dilation on the eigenspace. So what's happening is you take A times X, where X is in the eigenspace. So what's the dimension of your eigenspace, by the way? What's the dimension? There are two vectors in the basis, so what's the dimension of the eigenspace? 2. The vectors live in R3, but it's a two-dimensional, the dimension of the basis is 2. Okay, so now if you take A times the vector X, where X is in the eigenspace, that equals 2 times X. So what they're showing in figure 3 on the left side, they're just showing a two-dimensional space, the plane, the span of two vectors in R3 is a plane. But then look at the vectors. Then if you multiply the space, the eigenspace by A, that's like multiplying the vectors X, vector X by A in the eigenspace. X is in the eigenspace. A times X equals 2 times X. So what happens to the vectors in the eigenspace after you multiply them by 2? Look at the right side. What happened to the eigenvectors? It looks like they've gotten longer, right? Well, it looks like I want to be careful. Multiplying A times the eigenvectors equals 2 times the eigenvectors. And the transformation of the vectors on the left side gives you vectors on the right side that appear to be how much more longer than the vectors on the left side. They appeared, what did the transformation do to the vectors? It did them twice, double them. It doubled them. That's right, Solomon, that's right. And that's what I wanted to show you. So this example, this example, we've completed it. Are there any questions? Okay, all right, let me stop the recording.